Okay. I think it's recording my name now. Alright, in this slide, we have the types of van der Waals forces. What were van der Waals forces? Intermolecular or intra. Intra, right? No, not both. Intermolecular forces are called van der Waals forces. Okay, let's underline it. Okay, so the first type is dipole-dipole interactions. Second one is hydrogen bonding. The third one is London dispersion forces. Okay. Okay, among these forces, the strongest one is the hydrogen bonding. Strongest. Okay, and then dipole is the second strong. Okay, the London dispersion is the weakest. Okay, so which one is the strongest one? Okay. Okay, van der Waals force. We said that the strongest one is hydrogen bonding, and hydrogen bonding, okay, occurs between the hydrogen bonding, okay, occurs between the molecules that has nitrogen, fluorine, and oxygen. Okay. And of course, the bonding of these elements with hydrogen. Okay, nitrogen, fluorine, and oxygen. These elements make hydrogen bonding. About hydrogen bonding more when we come to that slide. Ion dipole interaction. What was, you remember the meaning for dipole?
Two poles, right?
Two poles, good job. So ion? Huh? No, thank you. So this ion dipole interaction, as you see, okay, in the picture, there is an ion, which is a cation at the center, and in the other one there is an anion at the center. Okay, and they are having an interaction with the molecule, okay, who has a dipole, okay, which is two poles, right? It is not very strong, okay, this interaction is not very strong compared to the others. As you see, we have dipoles over there, okay, dipoles. Can you read it, Hayden?
Dipole-dipole interactions. Molecules that have permanent dipoles are attracted to each other. The positive end of one is attracted to the negative end of the other, and vice versa. These forces are only important when the molecules are close to each other.
Okay. Dipole interactions. The more polar the molecule, the higher is its boiling point. And polarity is closely related with the dipole-dipole. So if the molecule is polar, that means we have dipole for its dipole. We have dipole forces on it. So as you see in this in the chart, the dipole moment, okay, you may, okay, look at here. We have dipole moment that is here, and the weakest, the smallest dipole moment we have on propane is boiling point is low. Okay, as you see, when the dipole moment increases, okay, the boiling point increases too.
So how do you get the dipole moment, or is it just a constant?
No, it can be calculated by taking the difference of electronegativity between the atoms. in the molecule. Okay, so the electronegative difference between the nitrogen is nitrogen is pretty electronegative. Okay, and there's a big difference between nitrogen and hydrogen and carbon's electronegative. That's why its dipole momentum is higher. The polarization is higher in this molecule. Okay, that's how we calculate. But I want to. All right, the next one is London dispersion forces. Okay. Yeah, medicine, read it.
London dispersion forces. While the electrons in the 1s orbital of helium would repel each other and therefore tend to stay far away from each other, it does happen that they occasionally wind up on the same side of the atom.
So, London dispersion forces form in a non-polar. Okay, it's very important. Let me take a note here. This is for not polar. This is for non-polar molecules. Okay, in this example, we have helium atom, right? And in helium atom, we may have like instantaneous polarizations, like at the time it happens, it's gone. It comes and goes. Okay, it happens sometimes, and it's not very strong. It's a weak force. And is it intermolecular force or intramolecular force?
Intra.
Intra. It happens in the helium.
Wait, what?
And
Part of the Van der Waals.
It is.
okay, let's go back then. What? Okay. Miranda, read this.
At that instant, then, the helium atom is formed, with an excess of electrons on the left side and a shortage on the right.
Okay, you see, normally helium is nonpolar, but it says at that instant, at the time, at that like 1 second. Okay, it behaves like there's a polarization. Okay, happens. It comes and goes. Okay.
Specifically in helium?
If it is on any molecule, as long as it's non-polar. Hydrogen bonding. Okay, so continue medicine.
Another helium nearby then would have a dipole induced in it, as the electrons on the left side of the helium atom too repel the atoms in a cloud of helium atom 1.
Okay, so as you see, in helium we have cation at the center, we have electrons, valence electrons around the nucleus, protons, and an interaction occurs. You see between the electrons of one helium with the protons of the other helium. Okay, so this is what London dispersion forces. But these forces are not very strong compared to the hydrogen bonding and dipole forces.
Just like, let's just say all of a sudden, where there's helium, so all of a sudden the atoms will shoot towards each other?
Yeah, and then that's it. I changed my mind. Factors affecting London forces. Miranda, read this.
The shape of the molecule affects the strength of dispersion forces. Long-speedy molecules like
Pentane.
pentane tend to have stronger dispersion forces than short-fat ones like neopentane. This is due to the increased surface area in fusion.
Okay, so if the surface area increases, that causes what? That causes an increase in London dispersion force or decrease?
Wait, say that again?
Okay, so if the molecule is long, that means you have more London dispersion forces or less?
More.
more stronger dispersion force than the short one. Yeah. So because the surface area, okay, increases too. Okay. Okay. Keep medicine. You read this.
Factors affecting London forces. The strength of dispersion forces tends to increase with increased molecular weight. Larger atoms have larger electron clouds, which are easier to polarize.
So, if the molecule is larger, longer, or heavier, it causes stronger London dispersion forces, right? Then London dispersion forces occurs on non-polar molecules or polar? Non-polar. Okay? So it occurs on non-polar, not polar. Okay, which have a greater effect? Dipole-dipole interaction or dispersion forces? Okay, alright. So again, let's repeat the difference between dipole-dipole and dispersion. What was it?
Dipole depends on.
Say it again, Miranda. Non-polar. That's the biggest difference. That is in a.
One is constant, the other isn't.
Good point. That's right. That's right. Good job. This is non-polar molecule. And this is, which one is constant?
The dipole is
Yeah,
constant.
constant. Not constant. Okay. Medicine, read it.
If two molecules are of comparable size and shape, dipole-dipole interactions will likely be the dominating force. If one molecule is much larger than another, dispersion forces will likely determine its physical properties.
Oh, you see? Not all the time, like the dipole-dipole is what? Is stronger. Okay, it depends on the what? The size of the molecule.
I need all National Honor Society students to the gym. National Honor Society students to the gym, please.
Dispersion will likely determine its physical properties. If one molecule is much larger than another, okay? If we are comparing a small molecule with, where are you going?
They said all National Honor Society.
Are you all? Okay.
What?
Okay, we have graphs here. In this graph, it is molecular weight versus temperature. Okay, so as you see, the molecular weight increases, the temperature or the boiling point increases too for the blue line. For the red, okay, yeah, it's a good graph. So let me. Okay, you see this? It is relevant. It is closely related to the boiling points, related to the molecular weight, right? Mm-hmm. But why the trend is like this for here?
Because water's weird. No.
Yeah, that's right. That's the answer. Because we have water here, and in water we have oxygen. Okay, at the beginning of this lecture, I said something like oxygen, nitrogen, and fluorine.
Oh, right. Mm-hmm.
And what were they?
Or the hydrogen bonding.
Hydrogen bonding is the strongest one. Okay, hydrogen bonding is the strongest one. That's why it's hydrogens. That's why water's boiling point is way higher than the others. 100 degrees Celsius. You have to give a lot of force. You have to give a lot of energy to break hydrogen bonding. That's why its boiling point is high. Okay?
Is that why the water is able to become a gas? Because the hydrogen bonding is so strong that boiling doesn't break it apart.
Yeah, the boiling doesn't occur, in a short time. So you have to bring the temperature to 100 degrees Celsius, and then that when the temperature comes to 100 degrees Celsius, the hydrogen bonding is broken. Okay, with that energy. Okay.
Please, Tanner Denty to the front office. Tanner Denty to the front office, please.
Okay, now we are gonna talk about hydrogen bonding. It's very important. Okay, so as you see, nitrogen, oxygen, and fluorine. No chlorine. Okay, chlorine is not a. So hydrochloric acid, we don't have a hydrogen bonding. Okay, as you see, medicine is hydrogen bonding intermolecular or intra? Inter. Thank you. Let's write it here. Inter. So which means we have a water here, right? And we have another water here. We have another water here. Okay? This is water number 1. This is water number 2. Okay. The electrons of the water number 1, okay, on oxygen, okay, interacts with the hydrogen of another molecule. Okay? And in this case, okay, in this case, no, not this. In this case, now there is an attraction between nitrogen. Okay, nitrogen is one of them. Between nitrogen and the electron pairs on nitrogen and the hydrogen of another molecule. So it's inter, not intra. Okay, the hydrogen bonding does not occur between this nitrogen and this hydrogen. What is this bond called? Yep, yeah. Covalent. Yeah. This is called covalent bond. It is not hydrogen bonding. Hydrogen bonding is this nitrogen and this hydrogen. Okay, and it's very, very strong. But covalent bond is stronger than hydrogen bonding because that is intra. Okay, so when we boil the water, Hayden, medicine, when we boil the water, we break what bond? Do we break covalent bond too?
No.
No, why not? How do you figure that?
Extremely strong.
It is still H2O because it's still H2O. Okay, we cannot. That it would be a chemical process if we were able to break the bond between hydrogen. This bond. This would be. We would change the identity of the substance if it happens.
So is this why liquid is like it is?
Exactly.
It's all.
Yeah.
Oh, bell ring?
No. It's time to go to the assembly, I think. Okay, so do you guys have any question on hydrogen bonding? So as you see, there's another hydrogen bonding here. The oxygen's electron pairs, and now the nitrogen's hydrogen is making an strong attraction here. This hydrogen bonding too. It happens between intermolecular,
mixture.